Hi, welcome to another Algebra 1 video. In this video we're looking at section 3.7, part 2, which is graphing absolute value functions. There's a link to part 1 of absolute value functions, section 3.7 in the description box. In this video we will learn about the general equation of absolute value functions, and we will also learn how to graph absolute value functions using transformations instead of table sets. Before we talk about the general equation of absolute value functions, we'll have to look at the parent function of all absolute value functions first. In part 1 of absolute value functions, we learned that the parent function of any absolute value equation is given by y equals to the absolute value of x, where y is your dependent variable and the x is the independent variable. We also learned that you can transform this equation in many ways, so we could come up with various examples such as y equals to the absolute value of x plus 1. So in this case, I'm transforming this function by shifting it upwards by 1 unit. You could also come up with y equals to the absolute value of x plus 7. In this case, we're transforming it upwards by a value of 7. Or you could come up with y equals to the negative absolute value of x plus 5. So in this case, we're reflecting this absolute value function across the x-axis and we're shifting it upwards by a value of 5. You could also perform a stretch on this function by multiplying the absolute value by a factor of 2. So y equals 2 times the absolute value of x minus 1 would mean that you're stretching this function vertically by a factor of 2 and you're shifting it downwards by a value of 1. But what you just looked at are simple transformations of absolute value functions. I'll introduce you to the general equation, which represents all of the transformations happening in the absolute value function derived from the parent function y equals to the absolute value of x. So the general equation for all absolute value functions would be a times the absolute value of x minus h, closing the absolute value plus k. In this case, your a determines by how much you're stretching or shrinking your function vertically. And then you have this h value, which determines by how much you're moving the function to the left or to the right. And you also have the k value, which determines by how much your function is being shifted upwards or downwards. A key thing to note from this is that this general equation is derived from the parent function because all of these a, h, and k values are performing transformations on the parent function y equals to the absolute value of x. Now that we know what the general equation of all absolute value functions is, we can learn how to graph these absolute value functions using the transformations. By knowing how to use the general equation, you don't have to rely on table sets and manually calculate the y value for every x value that you use to plot the function. So here I have my coordinate plane and I have the first function that we will learn how to graph using only transformations. We're given that y equals to the absolute value of x minus 2. So before we graph this, let's see what the a, h, and the k values in this function are. So beginning with the a value, we know that a is a coefficient of the x or the x minus h value. In this case, we know that our a value is 1 because we're not writing it on the side, because usually we don't write 1 as a coefficient. So we can say that the a value in this case is 1. Now for the h value, we're not given any h value because we're simply taking the absolute value of x. So our h value is equal to 0. What this means is that we're not shifting the function to the left or to the right by any unit in comparison to the parent function y equals to the absolute value of x. However, we do have a k value over here, which is negative 2 over here. So what this means is that we're shifting our function downwards by a value of 2 from the parent function. Now let's graph the function using these three constraints where a equals 1, h equals 0, and k equals negative 2 to graph the function y equals to the absolute value of x minus 2. So here I have graphed the parent function y equals to the absolute value of x in the green color. Now let's see what the function y equals to the absolute value of x minus 2 would look like when we graph it. From our first constraint, we know that a equals to 1, which means that we're not stretching this function by any factor. And it means that our function will remain the same in terms of the stretch factor, like the parent function y equals to the absolute value of x. Our h value is 0, meaning that we're not shifting the function to the left or to the right by any unit. Finally, we're given that the k value is equal to negative 2. Now this value of k equals to negative 2 will affect where our y-intercept will be for the function y equals to the absolute value of x minus 2. It's simple for this function, so we have only one transformation in this case, meaning that we're going to subtract all of the y values on this parent function by negative 2. Since our k value is equal to negative 2, this means that we're subtracting all of the y values or the f of x values on the parent function by 2. We're not shifting the x values at all because our h is equal to 0, and we're not stretching the y values because our a is equal to 1. On the parent function, we know that the function begins at the point 0, 0. So we can subtract the 0 on the y value of this point by 2, so that our new point on this function y equals to the absolute value of x minus 2 will lie over here. Now instead of plotting all the points that lie on the x-axis with their respective y values, we only have to graph 2 points on the either sides of the y-axis. We know that the parent function has a point of 6, 6, and since our k value is negative 2, we can subtract 2 from this 6 in 6, 6 to get 6, 4 for our new point. From our k equals to negative 2, we know that we can subtract 2 from the y value of this point. So our new point would be negative 6, 4. So now let's connect the dots and see what our function looks like and compare it to the parent function. So now in the red color, we can see what the function y equals to the absolute value of x minus 2 would look like. We can clearly see that the slopes of this graph are the same on this side of the y-axis, and on the left side of the y-axis they're also the same with a slope of negative 1. This tells us that our stretch factor has remained to be 1, and we have not changed the slope at all. We can also see that both of the functions lie on the y-axis, which tells us that we haven't shifted the function to the right or to the left. Finally, the only thing we have changed is our k value, which is negative 2. So this shifted the function from a y-intercept of 0, 0, which is also the origin. By shifting it downwards, we reached 0, negative 2, which is our new y-intercept. So now let's look at this second example of an absolute value function, which is y equals to 2 times the absolute value of x minus 1, closing the absolute value minus 2. So let's analyze what the a, h, and the k values of this function are. Straight away, we can see that our a value aligns with that 2 over here, so this tells us that we're stretching this function vertically by a factor of 2. We can also see that we have an x minus 1, which means that our h value is 1, and so our h value equaling 1 tells us that we're shifting this function to the right by 1 unit with respect to the parent function y equals to the absolute value of x. Finally, we have that negative 2 over here like the previous function, so our k is equal to negative 2, which means that we will be shifting the function downwards by a value of 2. So with respect to the origin on the parent function y equals to the absolute value of x, let's see where our first point will be transformed with respect to the origin. So we know that our h value is equal to 1, meaning that we will be shifting the 0, 0 to the right by 1 unit to get 1, 0 for our new point. However, we have a transformation which is a vertical stretch by a factor of 2. Now for the second transformation on the point of 1, 0, we know that we will be stretching it vertically by a factor of 2. We know that when we do vertical stretches, we multiply to the y value. However, in this case, our y value is 0. So when we multiply 2 with 0, our point will still equal to 1, 0. Finally, we have checked these two off, and we have the k value equaling to negative 2. So this tells us that we're shifting the function downwards by a value of 2. So finally the point will change to 1, 0 minus 2, which is negative 2. So this is where our point will be when we shift it from the origin because all of these transformations over here. And that point would lie over here. Now let's look at these two other points on the parent function which we already know are 3, 3 and negative 3, 3. So we will be transforming these 2 points to get the 2 points on the function y equals 2 times the absolute value of x minus 1 minus 2. So for this first point on the right of the y-axis, 3, 3, we know that we're shifting the function to the right by 1. So this means that this point 3, 3 will shift to the point 4, 3 because we add 1 to that 3 over here. Now we have the a value equaling to 2. So this means that we're going to stretch vertically for this point so that this point turns into 4, 3 times 2, which gives us 4, 6. So our stretched point would be 4, 6. Now for the last transformation, we have k equals to negative 2, meaning that we will be subtracting that 6, which is the y-coordinate of 4, 6, by 2. So when we do that, we get the new point of 4, 4, and the point 4, 4 will lie over here. Now we could do the same procedure to find the point which will be transformed from negative 3, 3 to some unknown value which we will find out. But we don't have to go through all that long process to find that point. Instead, we can see that the point negative 3, 3 and the point 3, 3 are reflections of each other with respect to the y-axis. So similarly, we can treat the point 1, negative 2 and the dotted line which could pass through that point as our new y-axis and then reflect the point 4, 4 to a point over here. we know that our y value will remain the same as the coordinate 4 because in the parent function we can see that the y coordinates are 3 and 3. So we already know that the y coordinate for the reflection of this point to the left of the y-axis will be 4 as well. The only thing we need to find out is by how much we're shifting it backwards along the x-axis so that we can push it upwards by 4 values. To find that x value on the left of the y-axis, we need to see the difference between the 1 in this x-coordinate and the 4, which is the x-coordinate of this point. We know that 4 is a distance of 3 from 1, so we need to shift backwards over here by 3 values from that 1. We already know that our y value is equal to 4, so we just have to subtract 3 from the x value over here. So 1 minus 3 is negative 2, which means that our x-coordinate will be equal to negative 2, and we know that the y-coordinate is equal to 4. Now we just have to simply plot the point negative 2, 4, and then we can simply connect the dots and form the function. And that point negative 2, 4 would lie over here. Now let's connect the dots and see what the function looks like. So this is what the function y equals 2 times the absolute value of x minus 1 minus 2 would look like in the red line. So this is what the function y equals to 2 times the absolute value of x minus 1 minus 2 would look like in the red color. In this case, the slope of this line would be positive 2 over here, to the right of this axis, which I've drawn in the dotted line, and to the left of the axis, the slope would be negative 2 because of the stretch factor 2. And this is it for section 3.7 part 2. This is also the end of chapter 3. Leave a like if you found this video helpful and subscribe for more videos in the future. And I'll see you in the next video as always. Thanks for watching.